We now want to spend a few minutes talking about the partition functions that arise from vibrations. And to motivate this a little bit, I want to draw a picture that I hope is familiar to you, but if not, it's one that you should be familiar with. And that is a graph of energy versus distance between two atoms coming together to make a bond. So let's say we're making a diatomic molecule, and the two atoms coming together, they're attracted to one another, their energy comes down as they get closer together, and then it hits a minimum, and then it goes up very steeply as they get even closer together. So this is a typical picture of the energy variance as two atoms come together to form a covalent bond. Now I draw this because what I want to call attention to is down here at the bottom of the well. We can think of this bottom as being like a parabola. And the parabola is really the potential energy surface that we associate with a harmonic oscillator. So in fact, when we talk about vibrations being like harmonic oscillators, we're really talking about this lowest energy region of the bond that is really behaving like a harmonic oscillator. Now we've already seen what the energy levels are for a harmonic oscillator. So I'll call those E vib, and they are functions of a quantum number V, and they're equal to h bar omega times V plus a half, and they go from V equals 0, 1, 2, up as high as you want to go. There's no limit to the bound states of a harmonic oscillator. All right, this h bar is simply Planck's constant divided by 2 pi. The omega is something that we normally report in wave numbers. So once again, we're using these wave numbers just as we did in rotation to talk about the energy levels, if you will, of a harmonic oscillator. Now the other thing I want to point out about this is when V equals 0, the lowest energy level is not 0, as it is in most of the other models that we've looked at, but in fact it's equal to 1/2 h bar omega. Now, I said this before, but I think it bears repeating. This is not energy that can actually be put to work any other way. It is a residual energy due to the wave-like nature, or I'll say due to wave mechanics. And it's not something that we can convert to something else. It is a vestige of the quantum mechanical nature of these bonds as they're formed. All right, so now how are we going to use these energy levels to determine some kind of partition function that we can ascribe to vibration? All right, well, once again, we would write it as a sum over the various energy states. And in this case, it's pretty easy because we'd just go from summation of V from 0 to infinity of e to the minus beta times the energies that are given here. So it'll be h bar omega times V plus a half. Now, one thing I want to do is kind of separate out this 0 energy from this, and I can do that by basically writing e to the minus beta h bar omega over 2 out front. Then the stuff that's in the summation is only the stuff that depends upon the quantum number V. All right, so it looks something like that. Now, one of the things that I should observe about this is that beta, which is basically temperature and the Boltzmann constant, h bar, which is Planck's constant over 2 pi, and omega, all of these things are greater than 0. So that means if I have something that's e to the minus beta h bar omega times some positive number, this is going to be something that's greater than 0, but it's also less than 1. So in other words, since this is raised to the negative power, I'm raising e to a negative positive number, so it's going to be less than 1. All right, now let's play a little what if. I'm going to set x equal to this number that is less than 1. So this is telling us that x is less than 1 here if I make this association. All right, now as I look at this summation of v equals 0 to infinity, and now I'm going to put in x raised to the v power, because that's essentially what we have over here is x to the v power. Now let me write out the first few terms. When v is equal to 0, I'm going to have x to the 0. When it's 1, I'll have x to the 1. When it's 2, I'll have x to the 2, and this is going to keep on going. But x is a number less than 1, so that means that each of these successive numbers is getting smaller. Also, this first number is just 1, so I've got 1 plus x squared plus so forth and so on, but each number getting smaller. Now, I'll appeal to your algebraic sense by saying if x were equal to a half, I'd have 1 plus a half plus a fourth plus an eighth plus a 16th. And you can get the idea. These are getting smaller and they actually have a limiting sum. In other words, this is not an infinite number. It's going to be a number that in fact is well characterized. And if you remember your study of geometric series, because that's what this is a geometric series, we can actually write down very quickly this sum is just equal to 1 over 1 minus x. All right. Now, one way you can prove that to yourself is multiply this 1 minus x times both sides. Multiply this stuff over here by 1 minus x, and you'll get 1 plus x squared plus minus x squared minus x cubed. So all of the higher order x terms actually vanish, and we end up getting just 1. All right. So another way to see this, another way to portray this is just equal to e to the minus beta h bar omega, because that's what x was equal to right here. Okay. All right, so now when we put this result into our summation here as part of z vibe, I'll end up with e to the minus beta h bar omega over 2 times this sum, but the sum is simply 1 over 1 minus e to the minus beta h bar omega. So what I have here is actually a pretty cute closed form for the vibrational partition function that is good for any harmonic oscillator. Now, having said all of this, I want to introduce again this concept of a temperature. So now we're talking about a vibrational temperature. And we're going to define it in a way very similar to the way we defined the rotational temperatures. In other words, I'm going to define my vibrational temperature to be a capital theta, and it's going to be equal to h bar omega over the Boltzmann constant. So once again, we're probably going to want to use the Boltzmann constant in terms of inverse centimeters, which I'll remind you was 0.6950346 inverse centimeters per Kelvin. All right, so now when we use this definition, I can actually rewrite z vibe in the following way. This will equal e to the minus vibrational temperature over 2 times the actual temperature divided by 1 minus e to the minus vibrational temperature over t. And this is one that if we calculate the vibrational temperatures, this becomes an easier way perhaps to evaluate the vibrational temperature. Now once again, I'll point out that when omega is large, that means that the vibrational temperature is large. And when that's large, that means the vibrational partition function is going to be very small. So when omega is large, then z vibe is small. And the opposite will be true when omega is small. So that means that when omega is large, I'm really not going to populate very many of the states in this harmonic oscillator. When omega is small, that's when I can have a lot more states available. But we find in practice for vibrations that these vibrational frequencies typically range from, say, 50 wave numbers up to, say, 4,000. 4,000 is probably a little bit high. But they're considerably larger than the rotational constants. This means that by and large, vibrational states tend not to be very highly populated. Most of the time we find most of the vibrations in a molecule, at room temperature anyway, to be somewhere around their ground state, or maybe just 1 or 2 states that are populated.